Hello everyone, my name is Elias. I'm a physics teacher from BGIS 1. Today, let us try to see the concept of electromagnetic induction, which is found on grade 12 physics textbook on page 266. That is unit 7 of the text. Therefore, the first subtitle of this unit, which is about electromagnetic induction, is the phenomena of electromagnetic induction. Just before going to describe the actual concept of electromagnetic induction, just let's define the concept of magnetic flux. Because or since electromagnetic induction and the laws of electromagnetic induction is expressed in terms of magnetic flux. Therefore, students, how can you define the concept of magnetic flux? How can you understand magnetic flux? Okay, magnetic flux is usually denoted by a Greek letter, and the name for this letter is phi. And magnetic flux is a measure of the amount of magnetic field lines that crosses or penetrates the region of area A. To understand the concept of magnetic flux, let's consider the following situation. Here we have source of magnetic field, which is a bar magnet, and as you know, this magnet has two poles, north and south pole, and the region around a magnet is known as magnetic field, you know that, and this magnetic field is a vector quantity. It has both magnitude and direction. To describe the direction of magnetic field of a magnet, we have to use arrow. This arrow is known as you know, magnetic field lines. So here we have a certain region of area A, or let's denote the area of the given region is denoted by capital letter A. And when we move the magnet towards the region of area A, as you know from your previous lessons, the magnetic field lines will emanate or will move from the north pole of a magnet to the south pole of a magnet in the outside part of the given magnet. So when we move the magnet very near or towards the region of area A, as you observe here, the field lines will penetrate or will cross the region of area A. And this situation produces a new physical quantity which is known as magnetic flux. That means whenever the magnetic field lines crosses any region of area A, this situation produces a new physical quantity which is known as magnetic flux. Mathematically, this one is magnetic field here. It's denoted by capital letter B and an arrow on its head to show it's a vector quantity. Therefore, mathematically, we can express magnetic flux as phi, which is equal to the scalar product of magnetic field and region of area A. If there is an angle between the normal to the region and the magnetic field, we use a cos trigonometric function cos theta. Therefore, BA cos theta is a mathematical expression of magnetic flux. Remember, in this case, B is the magnetic field, A is the area of the region, or if it is surface, the area of the surface, or if it is plane of loop, circular loop, the area of the loop, and theta is the angle between the magnetic field and the normal to the surface, not the magnetic field and the area. Because area is scalar, it has many direction. Therefore, theta stands for or represents the angle between the magnetic field and the normal to the surface. For example, if the field lines crosses perpendicular to the surface, it produces a maximum magnetic flux. But when the magnetic field or the field lines moves or crosses or cuts the region parallel to the normal to the surface, it produces this situation does not produce any flux on the given surface. So therefore, in order to observe the sign of magnetic flux, we have to start from the equation of or the mathematical expression of magnetic flux. That means, as you know, the SI unit of magnetic field is Tesla, it is denoted by T, and the SI unit of area is meter square. So therefore, Tesla meter square is the SI unit of magnetic flux, which is collectively known as Weber, and it can be abbreviated as W with small letter B. So 1 Weber, which is equal to 1 Tesla meter square. Therefore, in general, magnetic flux says it's a measure of the amount of number of magnetic field lines that crosses or penetrates region of any area A. The other one is electromagnetic induction. The students, what is electromagnetic induction? How can you understand the term electromagnetic induction? What situation or what condition must fulfill in order to produce electromotive force or a voltage or a certain coil of wire or across a conductor? Alright, so to understand the concept of electromagnetic induction, let's consider the following situation. Here we have a circuit, and this circuit contains, as you observe here, coil of wire. It can be solenoid, and it contains connecting wire and the sensitive galvanometer, which is important to read small amount of electric current. So as you observe here, if there is no external voltage or external potential difference exerting on the given circuit, there is no electric current flowing through the given wire. There is no electric current here, because there is no external agent or external potential difference, which is important to pump or to drift the electric charge to move around the given circuit. Therefore, there is no electric current and there is no movement of electric charge inside the given circuit, and the galvanometer reads 0 ampere because of no movement of electric charge at all. But now let's try to change the case. What will happen when we put a permanent magnet very near to the given circuit? What will happen? What will happen? So when we put a permanent magnet very near to the circuit, as we observed before, electric field lines starts to move from the north pole of the magnet towards its south pole. And to do this, the field lines must cross or must penetrate the area of the coil of wire on the given circuit. And this situation produces what? As you observed before, produces flux, and this magnetic field produces flux, and this flux produces electric current on the given circuit. But remember, simply putting or placing permanent magnet very near, or keeping the permanent magnet very near to the given coil of wire produces a constant magnetic field. A constant magnetic field produces a constant magnetic flux, and constant magnetic flux produces a constant electric current. And all this situation does not produce induced electromotive force. Therefore, our main goal is, or since electromagnetic induction is the process of or a way of producing or inducing electromotive force, therefore we have to change our case. That means now let's try to keep the circuit stationary and try to move the north pole of a magnet towards it. Or let's try to keep the permanent magnet keep stationary and try to move the circuit towards the permanent magnet. And this produces a change in magnetic field. What's the reason that we get change in magnetic field? Due to a movement of paramagnet towards a coil, or what's the reason that we get a change in magnetic field? Due to a movement of coil of wire or circuit towards a paramagnet. Because when we move a paramagnet towards a coil of wire, there is a different or a large number of a number of magnetic field lines will cross the circuit with time continuously. Therefore, this situation produces a change in magnetic field, and a change in magnetic field produces a change in magnetic flux. And this change in magnetic flux produces a change in electric current. And all these situations can produce electromotive force or a voltage. This voltage is known as induced electromotive force or induced voltage, because initially there is no electromotive force on the given circuit, but by using this situation or process we can induce electromotive force across a coil of wire or across a circuit. Students, let me ask you one question. How change in magnetic field produces a change in magnetic flux? Now let's try to go back the previous one. That means the equation of flux here. Once magnetic flux is expressed as BA cos theta, so in this case a constant magnetic field produces a constant magnetic flux, but a change in magnetic flux is occurred due to a change in magnetic field. That means if there is a change in magnetic field, there is a change in magnetic flux. If there is no change in magnetic field, there is no change in magnetic flux. That means a constant magnetic field produces a constant magnetic flux. So the magnetic flux is denoted by or directly proportional to the field. If there is no field lines that crosses the region of certain area, there is no magnetic flux at all. Therefore, generally, electromagnetic induction is it is a way of producing electromotive forces across a conductor by moving the bar magnet towards a circuit. Or, in other words, we can define or we can describe electromagnetic induction as it is a way of inducing electromotive force across a coil of wire by moving a magnet towards it. So remember, a voltage or electromotive force is induced whenever there is a relative motion that exists between the magnet and the circuit. If there is no relative motion between a bar magnet and a coil of wire, there is no electromotive force, or it's impossible to induce electromotive force. Therefore, the reason that we produce electromotive force on a coil of wire or a circuit is because of or due to a movement of bar magnet towards this coil of wire, or because of a movement of coil of wire towards a bar magnet by keeping a magnet stationary. Alright. The other important thing is here. The direction and magnitude of this induced electromotive force is described by two laws, and these two laws are known as laws of electromagnetic induction. So there are two laws of electromagnetic induction. They are Faraday's law of electromagnetic induction and Lenz's law of electromagnetic induction. The first one, Faraday's law of electromagnetic induction. Actually, this Faraday's law of electromagnetic induction describes about only the magnitude of the induced electromotive force, while the second law, which is Lenz's law of electromagnetic induction, describes the direction of the induced electromotive force. So let's see turn by turn. Faraday's law of electromagnetic induction. The Faraday's law of electromagnetic induction states that the magnitude of the induced electromotive force is directly proportional to the rate of change of magnetic flux, which is expressed mathematically as, or in symbol we can express it as, induced electromotive force is directly proportional to rate of change in magnetic flux. That means, I think you know the physical meaning of directly proportional. That means if the rate of change of magnetic flux increases, the amount of or the size of induced electromotive force increases with time. Or if the rate of change in magnetic flux decreases with time, it allows to decrease the amount of induced electromotive force with time continuously. If there is no change in if there is no change in magnetic flux, there is no induced electromotive force at all. This is the concept of directly proportional. And as you know from your previous lesson, physics lesson, in order to change, or if you want to change this proportionality sign into equal sign, it's always that we have to use a proportionality constant. For the time being, the proportionality constant that we use is capital letter N, change in Q over change in T. So as you know, always in physics or in science, if you want to change any proportionality sign into equal sign, we have to use a proportionality constant. This proportionality constant is important to balance the two terms of the given equation. Therefore, the proportionality constant that we use for this case is N, and this N is known as number of turns of coil of wire. N, capital N, is known as number of turns or number of loops of the given coil of wire. Or if you want to express the induced electromotive force in terms of change in magnetic flux, we can write as change in V a cos theta over with time. Good. So actually the reason that we call this first law of electromagnetic induction as Faraday's law, or the reason that we learn about electromagnetic induction is the concept of electromagnetic induction is one of the basic principles of operation of transformers, motors, generators. Therefore, if you want to understand the principles of operation of transformer, motor and generators, we have to have a good understanding or concept of electromagnetic induction. That's why we learn about this one. Therefore, electromagnetic induction was first discovered by a British physicist whose name is Faraday in the year 1830. In the year 1830. So now let's try. As you know, I think since electromotive force is its voltage, so if it is voltage, the sign of induced electromotive force is volt, and it is denoted by a small letter V. So now let's try to see the second laws of electromagnetic induction, which is known as Lenz's law of electromagnetic induction. As I told you before, Lenz's law of electromagnetic induction describes only the direction of the induced electromotive force, and it states that the direction of the induced electromotive force is always opposes the change that is causing it. Let me repeat once again. Lenz's law of electromagnetic induction states that the direction of the induced electromotive force is always opposes the change that is causing it, which means, or it can be expressed mathematically as induced electromotive force, which is equal to minus n change in Q over change in T. And this minus sign indicates or shows the direction of the induced electromotive force opposes the change in magnetic flux or the change in electric current. Or else, let's add another meaning of this mathematical expression, or let's add another meaning of statements of Lenz's law of electromagnetic induction. This Lenz's law of electromagnetic induction can be expressed in another way as once electromotive force is induced in a circuit or in a coil of wire, the circuit by itself does not allow or opposes any change in electric current. Let me repeat once again. Lenz's law of electromagnetic induction, or this mathematical expression, states that once electromagnetic force or once electromotive force induced in a circuit, the circuit by itself opposes or does not allow any change in electric current. So, and the other one is, if you want to describe the direction of induced electromotive force, we can use RHR rule, or the direction of induced electromotive force is or can be found by right hand rule. Right hand rule can be abbreviated as RHR, right hand rule. So by using method of a rule of right hand rule, we can easily describe the direction of the induced electromotive force. Therefore, based on the concept of magnetic flux and electromagnetic induction, let me give you one example. I think it's important for you to have a good understanding about magnetic flux. Here we have an equation which is about the concept of magnetic flux. So a magnetic field of strength, or the magnitude of the magnetic field is 0.4 Tesla, is directed perpendicular to a plane, circular loop of wire of radius 20 centimeter. So find the magnetic flux through the area enclosed by the loop. So to solve this problem, so we have to follow the usual procedure. That means first we have to pick out the given quantities. What are the given quantities from the given equation? So here we have magnitude of or value of magnetic field strength, which is PB, which is equal to 0.4 Tesla. And the other one, here we have radius, R, which is equal to 20 centimeter, or else 2 times 10 to the power of minus 1 meter. Okay. And the required. What are the required physical quantities? It is a magnetic flux. It is denoted by phi, which is equal to how much? Therefore, how can we define? How can we solve the given equation? So, if you want to solve the given equation, we have to use the equation of phi. The equation of phi, which is equal to BA cos theta. So here we have value of B, but we don't know the value of A. So to solve the value of magnetic flux, first we have to know the value of the area of the given circular loop and the angle that the magnetic field produces with respect to the normal, to the circular loop. Therefore, as you know, the area of the given loop of wire can be expressed as, you know, the pi r square. Therefore, you can use the value of pi 3.14 times radius here, 2 times 10 to the power of minus 1, the whole square. It becomes 3.14. This one, when we square 2 times 10 to the power of minus 1, we will get 4 times 10 to the power of minus 2 meter square. So when we multiply this one, the area becomes 0.13 meter square. Then now, and the other one is what is the angle that the magnetic field produces or makes with respect to the normal of the given circular loop of wire. It is perpendicular. That means the angle that the magnetic field makes an angle of 0 degree. So magnetic flux becomes, which is BA cos 0 degree. It becomes the value of P is 0.4 Tesla, and the value of area is 0.13 meter square, and the value of cos 0 degree is 1 times 1. So finally, the value of magnetic flux becomes 0.4 times 0.13. It becomes around 0.05 Weber or Tesla meter square. This is the size or the magnitude or the amount of the magnetic flux produced by the field that moves or penetrates perpendicularly to the given plane circular loop of wire. Therefore, the other one is, let me give you as homework from your textbook. So, page 280, physics textbook, page 280, review question. Question number 1, 2, and 3. So students, this is all about what the today's lesson looks like. So next time we will see about the concept of induction, the property of inductance, self-inductance and mutual inductance. Therefore, see you until next time. Goodbye.